Essentially, calorimetry is a measure of heat transfer or energy transfer within a chemical reaction or physical process. This two-part video series is going to look at that. In the first video, we're going to go ahead and do a series of practice problems that are leading up to a real-life demo. In the second video, we'll have that demo, which doesn't use a calorimeter, but does use the ideas of calorimetry, as well as the conclusion problem to that. At any part during the videos, I encourage you to pause whenever there's a question asked, work through it on your own, and then hit play to see the worked out solution. Enjoy!
Let's take the following reaction, the combustion reaction of isopropyl alcohol. In this reaction, 2 moles of isopropyl alcohol react with 9 moles of oxygen gas to create 6 moles of carbon dioxide gas and 8 moles of water vapor. Now, we know from previous lectures that the heat of reaction is equal to the summation of the heat of products minus the summation of heat of reactants. Now, there's been tons of experiments and experimental data that's been compiled to create standard heat of formation tables. So I went ahead and pulled these values up. You can look them up in the back of your book or online. Okay, so here I have the whole list of heat of formation values that we need for our reaction. There's 2 things I want you to notice. The first one is the states. It's very important that we have all the states written out. So we have isopropyl alcohol in its liquid form and all others in their gaseous forms. Heat of formation values will change depending on what state you're in. Now, I want you to notice that oxygen in its gaseous form has a heat of formation equal to 0 kilojoules per mole. That's because it's in its standard thermodynamic state. So once again, this emphasizes the importance of noticing what state we're working in. Okay, using these values, what should the heat of reaction be? So I want you to go ahead and pause the screen and work through it and then continue on to see the solution. Okay, if you got the heat of reaction equal to negative 2006 kilojoules per mole, you would be correct. So let's go ahead and work through that now. So we'll start with our equation. Our heat of reaction is equal to the summation of heat of products minus the summation of heat of reactants. So let's start with our products. We had 6 moles of carbon dioxide gas being created along with 8 moles of water vapor. So we can go ahead and take our heat of formations and drop them in. But notice we have to keep our molar values. So we have 6 moles of carbon dioxide gas, and therefore I'm going to multiply its heat of formation by 6. Whereas I had 8 moles of water vapor, so therefore I'll multiply its heat of formation by 8 moles. Okay, now I can work with my reactants. Over here, I have 2 moles of isopropyl gas and 9 moles of oxygen gas. So once again, I take my 2 moles and I multiply it by the heat of formation for isopropyl alcohol, and like we discussed, the heat of formation for oxygen gas is 0 kilojoules per mole, so that is just equal to 0 in our equation. When I plug all this in, I end up with negative 4,011 kilojoules. But notice, we are working with 2 moles of isopropyl alcohol. So this is equal to negative 4,011 kilojoules per 2 moles. So if I divide that out, I end up with negative 2,006 kilojoules per mole. Whoa! That's extremely exothermic! Assuming that this combustion occurs at constant pressure, which we're going to go ahead and assume, then we can say that we have now calculated Q and heat of reaction. But either way, it's extremely exothermic. So what can we do to lower this heat of reaction or the amount of energy given off? I want you to go ahead and imagine a towel soaked in isopropyl alcohol. With such a largely exothermic enthalpy change, it's very safe to assume that the towel would, when placing a flame, would burn as the alcohol combusts. However, to avoid such a reaction, we can pair it with an endothermic one, such as the vaporization of water. So therefore, we'll go ahead and create a mixture of 50 milliliters of isopropyl alcohol and 50 milliliters or 50 grams of distilled water. So let's go ahead and answer the following series of questions. The first one being, what is the heat of reaction or energy that will be released in the combustion of 50 milliliters of isopropyl alcohol? So step number 1 is find the moles. So we can look up the density of isopropyl alcohol, which is 0.786 grams per milliliter, and then we can go ahead and calculate out the molar mass, which equals 60.10 grams per mole. So we say hello once again to our best friend stoichiometry. I can go ahead and take the density and multiply it by the volume that we're working with, which is 50 milliliters, which leaves me with 39.3 grams. Now, when I take this value and multiply it by the molar mass, or 60.10 grams per mole, I end up with 0.65 moles. So step number 2 is multiply the reaction energy by the molar amount. So previously we had calculated that the heat of reaction, or reaction energy, to be negative 2006 kilojoules per mole. Multiply this by the 0.65 moles, and I end up with negative 1.3 times 10 to the third kilojoules. So very exothermic still. Okay, so now we're going to bring up a point that I briefly mentioned earlier. I want you to remember that Q is equal to heat of reaction at constant pressure, where the heat capacity of reaction is equal to the heat of reaction. So that means for us that we have a Q, or a heat capacity, which is equal to our delta H of reaction, or heat of reaction, which equals negative 1.3 times 10 to the third kilojoules. Okay, so question number 2 is how much of this energy will be absorbed by the water that we put into the mixture? We need to start by looking at this graph. So here, we can go ahead and see along the x-axis we have our heat input in kilojoules, and along the y-axis our temperature in degrees Celsius. And here we can basically see our different states. So we start with water in its ice form, and as we increase the temperature, then we transfer over into its liquid form and then its gaseous form. However, while it's changing states, it plateaus. There is not an increase in temperature. When we are linearly increasing, then we are calculating Q values. When we hit this plateau, or the changing of states, then we are calculating our heat of reactions. So in the first one, from ice to liquid, we have heat of formation, whereas in the second one, we have heat of vaporization, when we're going from liquid to gas. Okay, so we're going to go ahead and start with room temperature water, which is room temperature is equal to 20 degrees Celsius. So at 20 degrees Celsius, I'm in my liquid form. Okay, and we're going to go ahead and heat it up to its boiling point at 100 degrees Celsius, which means my first step is to look at Q. Okay, so that means we can use our traditional calorimetry equation. Q equals Cp times M times delta T, where Q, in our case, is equal to the Q of liquid, which is also equal to the heat of reaction at constant pressure. Cp is equal to the specific heat. The traditional units are kilojoules per kilogram Kelvin. However, we can manipulate these to meet whatever is easiest depending on the equation that depending on what we're given. So the traditional mass, or M, would be equal to mass, or in kilograms. However, if we were using a specific heat that was using moles, then we could go ahead and use N instead of M and use it in moles. Now, change in temperature, or delta T, is equal to TF minus TI. Okay, so let's go ahead and apply this to calculate Q of liquid. So once again, the specific heat can be looked up in tables, and the specific heat for water in its liquid form is 75.327 joules per mole Kelvin. Now notice we're working in moles. This means instead of using a traditional M, we're going to use an N, or put it into moles. So we're going to be using 50 grams of water. We'll multiply that by its molar mass, or 18.01 grams per mole, and get 2.78 moles. Now, my change in temperature is equal to TF minus TI. And remember we said we're bringing it to boiling point, so its TF is 100 degrees Celsius. And we subtract out its initial temperature, which is room temperature, or 20 degrees Celsius. This difference is equal to 80 degrees Celsius, or 80 Kelvin. Since we're working with a delta, or a change in something, we can directly convert between units, because the difference between 100 degrees Celsius and 20 degrees Celsius is going to be the same in the change of Kelvin. Okay, so I can go ahead and plug this into my formula, and I calculate that the Q of liquid is equal to 16.725 kilojoules. And unlike when I was calculating for the combustion reaction of isopropyl alcohol, I have a positive value here, meaning not exothermic, but rather endothermic, so absorbing energy, which is what we wanted to see. Okay, so that brings us back to our graph. We went ahead and took care of the Q liquid, so bringing the temperature up to 100 degrees Celsius. But now we have to consider what happens when I'm at that constant 100 degrees Celsius point, which is the heat of vaporization. Okay, so heat of vaporization of water is another constant value that we can look up. And this is equal to 40.656 kilojoules per mole. And when I multiply this by the number of moles that we're working with, or 2.78 moles, I calculate that my heat of vaporization, which is also equal to Q since we're at constant pressure, is equal to 1.13 times 10 to the second kilojoules per mole. If I combine this Q, so Q2, with the Q of liquid, or Q1, then I end up with a total of 1.3 times 10 to the second kilojoules per mole. And this is endothermic, meaning this is the amount of energy that the water is going to absorb when it's being brought from 20 degrees Celsius up to 100 degrees Celsius. Okay, so let's look at all of our values that we have. We calculated that the Q for the combustion of isopropyl alcohol was a very exothermic, negative 1.3 times 10 to the third kilojoules. And we calculated that the Q for the vaporization of water was a very endothermic, 1.3 times 10 to the 2 kilojoules. So when I add these together, I end up with negative 1.18 times 10 to the third kilojoules left. That's still the amount that the combustion of the isopropyl of alcohol is going to be giving off. So my final question that I'm going to leave you with is, will this combination then be enough to keep the towel from burning? I encourage you to go ahead and continue on to video 2 to find out.